list. I'm David Bader, and I'm a co-organizer along with Rich Murphy, who's up in the front here, and Andrew Lumsdane and Mark Sneer, who are not with us here today, and also a fairly extensive steering committee for the Graph500 that is a group of folks from around the world, from industry, academia, labs, who are curating this benchmark. As many of you know, this is an emerging effort to have a new benchmark related to big data problems. And again, I mentioned the International Steering Committee. Most of the names are up here. The idea about this benchmark was to give us another tool within the HPC committee to complement the existing benchmarks that we have to try to both measure and influence the design of high-performance computers for these big data problems. And Graph is a representative problem space where we often have very unstructured data, and instead of looking at floating point performance, we're often looking at memory subsystem performance, integer performance, and other aspects of the architecture. This is a new emerging effort, and we've had a few releases of the list before. Again, at ISC 2 years ago, we announced the formation of Graph500, and then at succeeding meetings alternating through supercomputing in November in the US and ISC here in Germany, we've now released up to today 3 lists, and today will be the 4th. It's a growing effort, and so we encourage everyone to participate. Right now, and today we'll release a list that has 88 entries. This is quite a success to go from our first list with only 9 entries on it now to 10 times that. And we're looking to grow, and hopefully by November we'll have 100 entries on the list and get to steady state with having a representative set of 500 entries over the next few years. It's also a benchmark where we're learning as we go. This is a complex effort, and we expect things to stabilize over the next few years. We're learning how to measure on these machines. We're learning about the reference implementations, the codes, the kernels, performance tuning, and so on. So this is a benchmark at its early stages, but already I think we've had some great success. It's been used in procurements that we're aware of. It's been covered in a lot of press. And so we're excited because I think it really is giving us some new data points for these emerging problem spaces in big data. There are a number of problems listed on this chart, 5 big areas ranging from cybersecurity, medical informatics, and looking through patient records, finding correlations with, say, billions of patients, understanding social networks and communities with them, for instance, analyzing Twitter data where we have streaming and unbounded data sizes, to data enrichment, symbolic networks, for instance, understanding the human brain with 25 billion neurons and how it operates. These are the canonical problems in the space where we have massive unstructured data sets, and they are often challenging to gain parallelism on because of the lack of locality in these problems, the size of the problems, and the operations are often memory operations where the bottlenecks that we face are in either local bandwidth to our memory or to our global memory in these systems. So the Graph500 has been launched. There's a website that you can find at graph500.org, and you'll find the latest list after it's released today. You'll be able to go and view it live. The website will be changing, so in November of this year you'll be able to play with your data a little bit more. And right now, currently we're ranking on a single kernel, which is looking at breadth-first search within a graph. We're planning to have, over the next few years, 3 kernels. The second kernel will be single source shortest path, and you'll hear more about that later today, and also for the list on November, the 5th list. But the first kernel, breadth first search, is going to be the ranking kernel. The others will ask for results, and we'll let the users of the website be able to understand how that data affects their application space. So breadth-first search is the first kernel, and that's a kernel where if we're given a graph, and a graph has vertices or nodes and edges that connect them, breadth-first search will start at one vertex and essentially traverse through every other vertex in the graph by following those edges. And the results are essentially the level sets of which vertices are reachable in how many hops from that source vertex. It's a abstract problem. It's a very simple problem, but it turns out to be a very useful kernel in many real applications. But it's also simple enough that those of you out there can, who aren't familiar with the graph space, can implement it and be able to compete. We also have reference implementations for shared memory, for distributed memory, and those are a good place to get started with that as well. So we think that this is a good kernel because even though breadth-first search sounds simple, start at a graph, one vertex, and just traverse through all the edges, it also creates a lot of challenges in our machine designs where we hit bottlenecks in those architectures, and also how to parallelize it on today's systems. So I want to move into the rankings that we have, and we have the fourth list, and I want to tell you a little bit about the results. So this is what you've all been waiting for. The number of entries on the list is growing, and we now have 88 entries on the current list. We are having some debate over the last couple lists on how to rank these entries, and I think at Supercomputing in November we have tried to stick to a very simple measure that we call TEPS. TEPS is traverse edges per second, and this is a canonic score of the amount of the performance rate of walking through a graph for a particular graph size. And we also have had discussions on these rankings, what are the ground rules. A lot of the influence of our decisions of our steering committee are made by the knowledge of other experts in the field. So we've relied on Jack Van Geer and folks from Top 500 to really guide us when we get to nuances of how to manage a list. And we're learning, so if there are issues that arise, please let us know, Rich, myself, Mark Sneer, Andrew Lumsdain, and we'll try to address those.
We make mistakes every time.
Correct.
So we try to fix them.
We've had some glorious mistakes, as some of you know, and our goal is to work through those, figure out what went wrong. When we had 9 entries, we could look at them by hand and evaluate them. But we have growing pains. We're scaling and we're having quite a success as we get our infrastructure to analyze potentially hundreds of entries. So we're looking forward to working with you as we keep expanding the list. I should say, after I go through these results in a very quick analysis, we'll have 2 additional speakers at the BoF. Torsten Höfler will talk about a new proposal for a green Graph500 that we're very interested in that will complement Graph500. And then Peter Kogi will walk through some analyses of Graph500 as well. So stay tuned for those.
No.
So we're going to present the top 3 results right now, starting with rank 3. And then I'll highlight the top 10. Those of you who have submissions to Graph500 who want your certificates, they're up on the table here. And after the BoF, you can swarm us probably outside the room because we'll have to switch pretty fast. And we'll try to pull out and hand you your certificates. So a drum roll, please. Okay. So the number 3 system on the list, just kidding. We had 88 entries, and I first wanted to say, before I go through the ranking, that we had a variety of countries. This isn't a US-dominated effort by any means. We have a lot of participation from around the world, including Japan with 11 entries, quite impressive, China, Russia, Switzerland, Germany, Netherlands, UK, Italy, Korea. So we expect to see a very international representation for the entries on the list, and we look forward to that continuing. There's nothing that is US specific about graph problems, so we're encouraged by that. Okay, now the top three. So in third place, if we could invite anyone up from University of Tokyo and Fujitsu team. So this is, and I'll let Rich here hand out the certificates. This is the Oakleaf FX system. This is Fujitsu Prime HPC with FX10. And they were number 3. We'll wait for the photo op. And they scored 358 gigateps. So that's... Okay. It's just in time for presentation. So we should, hold on 1 second.
So I count 3. 1, 2, 3. Okay.
Thank you.
And what's impressive also about this result is you'll look at scale. And scale represents the problem size. So scale 38 is the largest problem size that was solved. And this is log 2 of the number of vertices in the graph. So this is 64 billion vertices in the graph, and orders of magnitude more edges. So this is quite an impressive large graph. So the number 2 system is the DARPA trial subset of IBM's PERC system, Power 775 with the Power 7 processor, 8C running at 3.863 gigahertz. And this achieved over 500 gigateps, 508 gigateps on scale 35. So this is a very impressive result for performance. And if there's anyone from the DARPA/IBM entry here who would like to receive the certificate.
I think they said that they weren't going to be here, so maybe somebody else from IBM would be willing to.
We'll twist George's.
Yeah, George. George, do you mind sitting there?
Congratulations. On behalf of IBM.
There was an awful lot of interest actually in this entry because of the investment that went into making perks and cups.
Right, so this, as Rich said, is a very interesting platform from IBM, and all of the effort that went into designing this system is really a heroic engineering feat, so a lot of kudos to that. Now for the first place, we had a lot of discussion about the top ranking. And there's actually a tie for first place, and there was discussion about how to handle this tie. And this is where our steering committee, executive committee did a lot of discussion with how this would have been done on top 500. And we're following the same practices of top 500 here. So we actually have a tie for first place.
We actually emailed Chuck and Gara for ruling it.
Yeah, so when we couldn't decide at all what to do. It's a very complex, well, I shouldn't say very complex, but there's a lot of factors involved. And we did exactly what Jack would have done with top 500, and his email was there, helped us decide what to do. So we have 2 systems. The first system in the ranking is the Department of Energy and Argonne National Labs mirror system. And again, this is IBM Blue Gene Q. And also in first place is Livermore Sequoia Blue Gene Q. So these are subsets of the full system. And in this case, there are 2 organizations that have this result running on the same architecture, the same hardware, and also with IBM support. So these are 2 separate entries that both achieve 3,541 gigateps. This is quite a substantial number, again, on the largest problem size that was solved for this ranking. Scale 38 is 64 billion vertices. This is a huge, massive graph problem to solve. So we'd like to recognize both of these trying to give them equal time up here as I flip back and forth.
So